Okay, welcome back, everybody. The topic today is a continuation from last week, and I'm going to do some kind of repetition of some of the topics, and then I wanted just to complete this discussion about the Fokker-Planck equation and the Langevin equations, which are used as calculational entities in the setup of the variational Monte Carlo code with importance sampling. So what you're going to see now is something you can just forget about in a certain sense, because we are not going to dive into the usage of these derivations. We're just going to take these derivations, and I bring them up here just to give you the kind of mathematical background which leads to the Fokker-Planck equation. Now, the Fokker-Planck equation, as we discussed last time, is a modification of the standard diffusion equation, where you can think of, in addition to a standard kinetic energy term, you have a particle which moves under the influence of some external force. Now, we are going to use this equation as an aid in order to set up importance sampling, because that's going to give us a transition probability which follows the wave function. So that means that when we jump around in space, when we place our random walkers, which sample all the possible positions, we are now going to guide them according to the probability distribution which we have chosen. So this is just a quick reminder of the more overarching topics. Then, in order to find the new positions, there is an equation which is intimately linked with the Fokker-Planck equation, which is called the Langevin equation. And for those of you who have studied, let's say, statistical mechanics, you may have encountered these equations, because it's a way to actually set up Newton's equation of motion with a stochastic term in addition to the standard force which the particle moves under. So the Langevin equation, you can think of that as a stochastic equation of motion. So you would have a particle under the influence of a force, and at the same time, you have some stochastic noise. And often this is just modeled as a Gaussian, because you have basically no idea what the noise looks like. Then there are some programming technicalities, which I wanted to bring up, but these are technicalities which you will need when you're setting up the correlated part of the wave function. But I wanted to bring them up now so you have them for reference for later, because when we are developing the machinery, we are testing everything on a non-interacting case. The non-interacting case is easy to set up, and it's easier to set up, and it's easy to test against an analytical solution like the harmonic oscillator. So the harmonic oscillator is one of these classic examples. Then comes the new element. So the first two elements of the lecture today are just more background, which you may not need immediately. But then the optimization part is the one which becomes interesting. So I'm going to use the first lecture on these technicalities, and you will just be overwhelmed with slides. I hope you will survive the first lecture. But then the optimization part, which we will start with in the second lecture, is the one which becomes important for us, because that's the piece which is relevant for the way we find the optimal variational parameters. So the way we have been doing it till now has been as a brute force approach, where we make an array of variational parameters. And then for each of these parameters, we run a heavy duty variational Monte Carlo calculation with, let's say, 1 million or more cycles. And for many of these points, they are actually away from the minimum, which means that we are wasting cycles, just a waste of CPU cycles. You can do this in a brute force and just use all the point to interpolate and find the minimum. But the standard approach is actually to optimize the energy. And then with the optimized energy, which means that we need to calculate the gradient of the energy with respect to the variational parameters, then we find the minimum when the gradient vanishes, as usual. And then when we found the minimum, that's when we mount the large-scale Monte Carlo sampling. So you will typically use some 10,000 iteration points for every gradient calculation. And then when you find the minimum, then you start your Monte Carlo calculation with millions or even billions of Monte Carlo samples. So the optimization part is an important technical aspect, which simply saves us CPU cycles. There is no point in running a heavy-duty calculation away from the equilibrium, or where you have the minimum. And for those of you who have taken a course in machine learning or taking courses in machine learning, you have encountered the optimization part. And you will recognize the lovely gradient descent with different types of optimizers, learning rates, for those of you who are familiar with these concepts. So this is nothing special. It starts with Newton method, and then you develop different gradient schemes. So for some of you, this is going to be familiar, except that now the gradient is going to be the expectation value of the gradient of the expectation value of the energy. So for those of you in project 2 who would like to deal with neural networks, then you need to optimize a function which, instead of just some few variational parameters, has hundreds of thousands of parameters. So for a neural network, then the trial wave function would be a neural network. And the quantity you optimize is the energy of the system as a function of the parameters of a neural network. So the only thing which changes is that you have a much more complicated function. But you know that neural networks, if you make a comparison with us, we are very good at finding patterns in 3 dimensions, because we've had millennia or even millions of years of evolution where our ape brains have been trained to recognize dangers in 3 dimensions. A neural network finds the same patterns in huge dimensions equally well as it does in 3 dimensions. So the neural network is actually, as many of you know, it's a very efficient way to find patterns in multi-dimensional objects. Okay, that was a kind of small digression. So the topics on convex optimization is something which we will look more into next week. So today, if we get into gradient descent, that's roughly where we will stop today. And then next week, we will discuss some other methods which are also used in these type of optimization problems. Now, the thing I wanted to remind you now is a little bit about what we discussed last week. So we have a probability distribution, and this is linked with the Metropolis-Hastings algorithm. So you could think of you having an initial distribution, which is just given by a Kronecker delta. Alternatively, you can go to the continuous case and you can have a delta function. This could now be your initial condition or your initial distribution. And then the standard Markov process is us jumping from a time t equals 0 in a time step delta t to a time t. And this is the equation for the Markov chain, the discretized case. And then you can make that continuous. So there's nothing which hinders you to have a continuous probability distribution. So then you start with a probability distribution here, and then you have a transition probability, and that brings you over to the new probability of being at a state in a state y at a time t plus delta t. So this is nothing but a continuous variant of the Markov chain, okay? And when equilibrium has been reached, what happens then is that these probability distributions become time independent. There may be a time dependence on the transition probability. And we simply write it like this. This is a probability of being at y, given that you start at x. So the bar here is a conditional probability. So the probability of being at y, given that you started at x at a time t. What we did last time was actually to, so this is just a reminder from last time, is that this probability distribution is something you can relate to its Fourier transform. And for the diffusion process itself, when you make a Fourier transform of the diffusion equation in space to momentum space, then you can solve it analytically. So it means that when you use the definition of the delta function, you would then have a probability distribution in momentum space, which is just 1 divided by 2 pi. It's actually not so difficult to show that. And that means that you can then find the solution to the diffusion equation without an external force, which is then simply given by this equation, which you can integrate up, and then you have a standard Gaussian here, period. So that's the one of the things which we did last week. And then with the Fourier transform, you can integrate back again, and then you will get the standard equation, which you have seen many, many times for a Gaussian. And this is the Gaussian in space, and the one here is just the Gaussian in momentum space. So a transformation of coordinates doesn't change the probability distribution. A Gaussian stays a Gaussian. And the next thing which we did was actually to look at the diffusion equation again, because this probability here is also the solution to the diffusion equation. And this is normally called the generalized solution to the, or the universal solution to the diffusion equation. And this represents a probability of being in a state Y, a transition from a state X to a state Y in a small time step. Now, the problem with this one, when we place that one into the metropolis sampling, then this is reversible in Y and X. So when we take a ratio, when going from X to Y or Y to X, that ratio gives us 1. So that's why we introduce the Fokker-Planck equation. So what you will see here, just some preliminary steps towards the derivation of the Fokker-Planck equation. So I just wanted to bring that in so you can see how you think when you derive the Fokker-Planck equation. And in this particular case, what we have is a probability distribution here at a time X, at position X at time T, which is now given by this integral here. We start with a time T prime, and we integrate over all positions in space. You can do the same thing with a new one at the T0, and then you can have a new one at T prime, so you would simply have times T0, T prime, and T. So all these equations are representing a transition probability to a given time, given a specific initial time. And this is something you can combine. You can actually combine these equations, and that leads to a famous equation, which is called the Einstein-Smoluchensky-Kolmogorov-Chapman equation, where you now can relate these transition probabilities by going from a time T0, you go to intermediate step T prime, and then you integrate away all the spatial positions, and that gives you the final transition probability. And you can actually replace position because you can Fourier transform that one to momentum space, or you can then think of momentum as replaced by velocity, because the momentum is given by, so velocity is given by momentum squared divided, the velocity is given by the momentum divided by mass. And the kinetic energy is momentum squared. And you can then replace, you can choose whether you want to deal with velocity or momentum. The only difference then is that you have a mass as a constant, which you can then scale away. So I'm now going to replace positions with momentum. So this is nothing but a Fourier transform of your quantity here. So that's another possibility. So if you think of the Fokker-Planck equation, the equation you would start with is actually this one. And then I'm going to make some small redefinitions. So I'm assuming that these quantities depend only on the differences in time. So this is T prime minus T0, which is this quantity. So this probability will depend on the initial position x0 and a time difference at T0 minus T prime minus T0. And this time tau is then simply the time T minus T0, which is S plus tau here. So this is just T minus T prime. So you can rewrite this equation here just in terms of this new time variables S plus tau. And then the whole idea now is that you make a Taylor expansion, essentially doing that, and you assume that this tau is very small. So what you're doing then is to look at very small changes in time. So that, and one of the reasons you do this is that you then can assume that the probabilities don't change much when you move from a small time in a small time step to a new time. So that means that the shape of these probability distribution do not change that much. If you do that, you can make a Taylor expansion in terms of a small step size, where this is just simply given by x minus some quantity g. And that means that you can rewrite your transition probability plus some derivative term here. And this is simply going to be given by this expression here, where you just made a small expansion of this quantity here around this variable s. So this is nothing but you just making a small Taylor expansion. And you assume that this quantity here takes non-negligible values only when this quantity is small. Actually, this is the same as we discussed earlier, which is called this master equation. So if you then think of a Taylor expansion, then you just need the higher derivatives. And that means that this quantity here can then just be written out as the higher derivatives, an expansion in terms of higher derivatives of this quantity here. Okay? And if you do that, you can take this Einstein-Chapman equation and rewrite it. So you would have a term here, which is the probability, which you had on the right-hand side. So I'm singling out this term here. And if you neglect higher powers, then you end up with an equation where you can actually, if you take this here, if you expand this one, you can actually end up with an equation which looks like this. So if you now move on to the next one, doing the Taylor expansion, you introduce some moments here, so which are simply given by these higher derivatives. So this is just a manipulation with Taylor expansions. Then we end up with a probability distribution with respect to time here, the derivative, which is now given by this Taylor expansion. And when you let this tau go to 0, you also assume that this quantity here is moving rapidly to 0. And that means that you can approximate this equation in terms of this equation here, and then the second derivative. So the second derivative is going to play the role of a standard diffusion term, whereas this term here is the one you will interpret as a force term. So if in a more compact form, this is actually the Fokker-Planck equation, where this one is your standard diffusion term, and this is going to play the role of an added force, which is then normally can be replaced by some external force which the particle is moving under. So this is the way you would derive the Fokker-Planck equation. And then you would recognize this m1 here times w as a force, and this m2 then times w is then going to be the standard diffusion term. This is the way you actually proceed in setting up the Fokker-Planck equation as a modification of the standard diffusion equation, where you actually start with the standard equation for the Markov chain. So you start with a Markov chain equation, and then you can derive a modification of the standard diffusion equation by a Taylor expansion. So originally, you can, if you leave out this Taylor expansion, you can derive the standard diffusion equation from a Markov chain. We are not doing that here, but I'm just stating that this is something you can do. Now, the next thing is this Langevin equation. And this is an equation which you will encounter in many, many applications in fields like fluid mechanics. You will encounter that if you're thinking of particles suspended on a liquid, which make Brownian motions. So the way you can think of this is if you think of a particle suspended in a liquid, on its path through the liquid, it will collide with the molecules in the liquid. And then on average, the particle will collide more often on the front side than on the back side. So it will experience a kind of systematic force which is proportional to the velocity. So this is just a model which I'm making. You know very well that if you look at a particle moving in air, there can be a drag term or air resistance term, as we call it, which can depend, depending on the velocities the system has, on the velocity or on the velocity squared. And this is something which you probably have encountered when you follow the course in mechanics. So there will be a systematic force, which is proportional to the velocity, which could be this one. So this is what you're having here is actually you rewriting Newton's equations, and you're looking at the first derivative. So you take Newton's equation, which is a second order equation, and you write it out as two coupled first order equations, one for the position here, which is the velocity, and then this is the acceleration, right? So let me just bring that back so you get a small reminder of what you're doing here. So let me just switch quickly to the whiteboard so that you have a reminder of what is going on here. So if you think of Newton's equation, suppose now that you have the standard equation. So they have and we are looking at the equation just in one dimension. And what you would have then, you could have a friction term, which is a dx, first derivative. This is nothing but your velocity. So I'm looking at this in one dimension. If you're looking at harmonic oscillations, so you could think of harmonic oscillations like a pendulum, or just your particle moving in a harmonic oscillator term with some friction. So this term here is normally called a drag term or friction term. And then if it's moving in a harmonic oscillator, there will be something like x of t, and then you can apply an external force, which depends on time. If you think of the pendulum here, then the variable x is replaced by the angle which the pendulum has with an axis. And then you would have a term which would go like sine or cosine theta. So that would be a nonlinear equation in the unknown quantity. If you're thinking of a particle which oscillates in a harmonic oscillator, then the position term will be given by this one. There will be some friction, which will dampen the motion. And then if you apply an external force, then this external force will force the system to oscillate in a specific way. So you're probably familiar with if you have, let's say, a kind of damping. So if you put the force equal to 0, then typically you would have some initial condition. So this is the position x. As a function of time, you would start at x is 0 here. And then the system could oscillate like this. And then at a certain point, it just dies out. And that's because you have a resistance term here. If you, on the other hand, if you add an external force, so this would be the case with a force equal to 0, but then you can add an external force. And what happens then is that you could start at the same position, and then it goes down, and then suddenly the external force kicks in, and it oscillates like this for the rest of life. So this would typically be the f of t different from 0. So in the beginning, the drag term, which you have here, the resistance term, tries to kick in, but then after some time, the force takes over, and the system oscillates, for instance, with this frequency of the force. I guess this is just a quick reminder from your mechanics classes. And then you know that this equation which you have here is an equation which you can rewrite in terms of an equation for the velocity. So this is one differential equation, dx dt equal to v. So you can rewrite a second order differential equation in terms of two coupled first order equations. And that means that the second equation becomes like m dv dt, that's the acceleration. And then I have this eta, which is a material specific constant times velocity, plus x is equal f. I guess you've seen this kind of equations before, right? So let's go back to the slides then. And so let me just bring them up here. Sometimes when I go full screen here, it actually does a something for me which I don't want. Here we are. Can you online see the slides? Should be able to see them here. Yeah. Okay, let's go full screen again. So what we have then is a position part, which now is just a velocity. So that's one of the differential equations. And in this case here, we have a velocity-dependent term plus some force. And we took away this harmonic oscillator term, x. So that means that you can think of your system having something which is given by the velocity. There is the force term here, and then you have a stochastic force here. And that's the basis for this equation here. And from hydrodynamics, you can actually find an equation for the friction constant, this quantity xc, which you can then relate to the viscosity of the solvent, and this A can be the radius of a particle, if you think of a particle as a sphere. So this is a standard equation which you may have seen when you took a course in mechanics. And this is an equation which you then, if you look at this equation here, you can integrate up. And when you integrate it up, it just becomes this equation here. And if you want to get some useful information, what you have to do is to take the average of all possible realizations of f with initial condition with initial velocity as a condition, an initial condition. And a useful quantity is then to calculate this quantity here, which then, when you now look at the equations, you assume now that this stochastic force is chaotic in character, which means that this expectation value is equal to 0. So it just averages out. But then you have a correlation term where you relate a time t prime and a time t, which then can be given by a delta function. This is just an assumption. If you do that, then you end up with, if you use these equations here in the calculations of these terms here, then you can find an equation for this correlation of the force at the time t prime and t, which is given by this quantity here. And if you then go back to the Langevin equation, you can then find a term here. If you take and integrate up the velocity, then you can find the position. So this new position at the time t is given by the previous position plus some additional terms here. And you can actually calculate the mean square displacement if you want to. But this Langevin equation, if you now think of what we are setting up here, is actually a term here which now would depend on this external force, which we then can use in updating the positions of the particles. So we will start with an R0. There is some term here which is, and here, which is depends on this stochastic force. And then we have the new position. So this is the kind of background which is often used when you link the Langevin equation with the Monte Carlo samplings, which we are doing. So that was just meant to give you a kind of background in what we are doing. Now, if you want to read more, this is actually an extensive topic in classical mechanics and transport theory, which we are not covering here. But I hope that these kind of small derivations can give you a feeling of how we set up the update for the particles and where the Fokker-Planck equation comes from. Now, the thing which technically is more interesting for us, and this is for later. So when you are going to include the Jastrow factor, there are some considerations which are useful to think of. Because when you're moving many particles, then the calculation of this function here, the correlated part, can become quite involved. And there are some tricks which then can allow us to speed up the coding. So the wave function which we are dealing with, the correlated part, is often expressed in terms of an exponential. So when you're doing a neural network, you will often just replace this with a network. Or you could actually keep the exponential, which in many cases makes the ratios in the variational Monte Carlo sampling easier. and replace this function f with a neural network. So what you need is the gradient of this quantity here when you're calculating the quantum force, but you also need to calculate the local energy in an efficient way. So that means that when you look at this quantity, which is a standard way to represent this Jastrow factor, we need these quantities in many places. So one place where we need it is when we take the ratios of the metropolis test, and then we have the one body part, which is easy. In our case, in the first parts of the code which we're developing, we don't have this correlated part, but we have only the one body part, which in our case is the harmonic oscillator. And the harmonic oscillator is given by exponentials. So we would not calculate exponential of x new divided by the exponential of x old, but we would simply calculate the difference between the numerator and the denominator as arguments, and then evaluate the exponential. This also applies to this quantity. But you see that since this acts on two particles at a time, this is something we have to be a little bit careful with when we calculate, okay? So these are some considerations which you need to keep in mind when you implement the full wave function. We are now doing the harmonic oscillator first, because the harmonic oscillator is simple and it has analytical solutions, but at the end, we have to add the correlated part. So if you look at the calculation of the quantum force and the local energy, you need this quantity, the gradient, and you also need the second derivative of the trial wave function. So if you look at the gradient, you need these quantities here, and this is what you have already, but then you need to include this one. And then when I look at the kinetic energy, I now calculate the kinetic energy of a given particle. So this is an expectation value we are evaluating, and we need to evaluate this quantity which you see here. Which means that for the kinetic energy, we are going to need again the gradient we calculate with the quantum force, because then we need to take two vectors. So these are two vectors which we need to multiply. So till now, we are living happily without any complications, because we are not including these three terms. We are just looking at this first term. So everything which follows here now for the rest of the lecture are complications which we need to think of for later. So there are ways to set this up. So if you think of this function, there are some efficient tricks which you can use in setting it up. Essentially, we are going to look at a function which depends on the relative distance between two particles. So the typical form which you often encounter, so when you have two particles which repel each other with a Coulomb interaction, you can then show that the minimal ansatz for the trial wave function is that you have an exponential which depends on the relative distance. So this quantity here is now given either by this one, if you are in 3 dimensions, or the second one if you are in 2 dimensions. This is a quantity which is not defined for I equal to j. So that means that we don't need to store that quantity. So it means that what you need to store when you're moving the particles, so when you move a particle at a time, you don't need to store the quantities below the diagonal, because if you look at what you have here, these are the same if I interchange I and j. So there is no point in storing these values. So you would just store an upper triangular quantity. And on the diagonals, you just have zeros. So it's only these quantities which you need to consider. So if I'm moving particle 1, then what changes are all these quantities. But the other ones are unchanged. So just keep that in mind when you now are moving particles. We would typically move a particle at a time, because that gives normally a more efficient code. So we will move one particle at a time, and suppose that you have the K particle, and this sampling will be seen to be particularly efficient when you're in project 2, if you want to include a Slater determinant. So this is for project 2, actually. So these are just technicalities. It's not very exciting, but I'm listing them because these are things you could think of when you're now encoding the correlated part. Especially if you have more than 10 particles, then this is going to be time consuming. So this ratio is actually going to be given by the new one and the current one. And if you move one particle at a time, as I said here, there is only one set of entries which will be changed. So if I'm moving particle 2, these entries will be changed, but I also have to pay attention to this one. Okay? So what you need then is actually something which, since you're using an exponential form, you have this new guy and the old one, where this delta here is just the difference between the old one and the new one. So you don't evaluate two exponentials. You just take the difference between new and old, which means that you actually have these quantities here. So that means that if you're just moving one specific particle, there is only a specific contribution here which kicks in. Okay? So you need to develop an algorithm which runs only through the elements of the upper triangular matrix and have k as an index. And the expression to be derived is something which then is of interest both for the kinetic energy and the quantum force. So the quantum force for a given particle would then include terms like this. So here I have skipped the vector signs. So this will be particle I, but in principles, these are, we are calculating the gradients with respect to the different particles. So if you look at this quantity here, and you now move one specific particle, then you can actually simplify these equations, where you now simply, when you look at the ratios, for the first derivative, there are only n-1 terms which survive because the terms g that are not differentiated cancel with their corresponding ones in the denominator. And that is something which is useful to look at. So we are just anticipating a complication which is coming, but I wanted to bring this up for completeness because this is something where we need to think a little bit more carefully. But so take a look at these expressions. I mean, when you see them now, it's not so exciting, but you would need to think a little bit more carefully. And the reason why we are putting this up is that the typical form is going to be given by an exponential, which means that, so if you now look at these terms here, an equivalent equation is obtained for the exponential after replacing g of ij with this function f, because then you can also use symmetries here, because this is symmetric. Then you can get expressions where all the derivatives acting on the particle are represented by the second index of g. So that means that when we calculate this quantity here, we can actually rewrite it like this. And for the exponential case, you end up with an equation like this, because you have an exponential. Then the correlation form depends on the scalar distances, and then you can use a chain rule. So that means that when you look at the calculation here of xj, you can use a chain rule and rewrite it in terms of the relative distance. And that means that you get this specific term here, where this rik is now the relative distance. So that means that you arrive at an equation for this quantum force, which looks like this. Then you can set up explicit equations. So if you have the standard correlation form in terms of an exponential, these terms can be manipulated further, and you're actually getting a quantum force, or one of the elements, which is now given by these two terms here. And what I'm setting up now is also the same equation for the second derivative, which you will need when you calculate the kinetic energy. And you can do similar manipulations. And at the end, you get, if you have this specific form, you have an equation for the kinetic energy for the correlated part, which you need to plug in, which is then going to look like this, which then depends on the relative distance only. So this is one of the equations which you will need to encode when you include the quantum force and the correlated part. So you would need this term, but you also need an equation for the first derivative for the correlated part of the wave function. So this gives you the gradient. And if you go back to the equation which we put up here, when you're setting up the second derivative, you actually need a dot product between two vectors, two gradients. So the quantity you calculate in the quantum force is also something you will need when you calculate the kinetic energy. So these are technicalities. It's not the most exciting thing, but it's a technicality which we need to think of because it makes often life easier. But if we use automatic differentiation, then we can just let automatic differentiation do these derivatives. But you should keep in mind then that if you use automatic differentiation without thinking, that may often involve many more cycles. So if you do some thinking and look more carefully at the form of the wave function you have, you end up with derivatives like these ones, which you then can calculate with automatic differentiation. So if this F is a neural network, then you will need to take the derivative of a neural network. Okay? But the typical form which you have is an exponential of some function for your correlated part. Okay, so what I wanted to do next is actually to look at these gradient methods. And this is a topic for the next lecture. So just view this one as a kind of technicality. The thing with the Fokker-Planck equation and the Langevin equation is something you can just think of some background information, whereas the derivatives of the correlated part is something which we will need to code later. So I'm just adding that one for the sake of completeness. But now we are going to dive into the next element. So we did brute force Monte Carlo sampling. We have importance sampling. And now we need to deal with the optimization part so that we don't waste CPU cycles on parameters, variational parameters, which are far away from the minimum. So that's the overarching kind of goal which we want to implement. So we're going to take a top down with a simple harmonic oscillator. So you see the basic ingredients, because that's something we can calculate analytically. And then we are going to look at how we can implement this for a quantum mechanical example, which in my case is just two electrons in a harmonic oscillator trap, plus a Coulomb interaction. And the Python code here is just meant, which we're going to discuss after the break. So after the break, I'm going to switch between the whiteboard and the Jupyter notebook. And then this is something which we will probably look more into details next week. Take a small break. So welcome back. So the second half of today's lecture, and this will also be the topic next week, is to set up the optimization part. And the rationale for this, the motivation, is that we don't want to waste cycles away from the minimum. So we are going to calculate the gradient of the energy in order to find the minimum of the energy as a function of the variational parameters. And then when we have these optimal values, that's when we perform a large scale variational Monte Carlo calculation. As I said in the previous lecture, there's no point in us running billions of Monte Carlo cycles away from the equilibrium point or where we have the minimum. And this means that we are going to derive a standard gradient descent, which is based on Newton's method for finding the roots of a function. The roots, in our case, will just be the gradient. So where the gradient is 0, then we have reached that point. There are other methods which are called steepest descent and conjugate gradient methods, which are very efficient if you can calculate the second derivative. For the variational Monte Carlo case, which we have, these second derivatives are quantities which we can often set up, but you will see that these become more in computational intensive because we are going to invert a matrix, etc. And this matrix is called the Hessian in statistical analysis when we are doing optimization. And that matrix can be large if we have many parameters. And then we are trying to circumvent that. And there are many ways by which you can do that. And one is called the quasi-Newton method, which is named Broyden's method. And then there are variations of Broyden's method. And these are methods which we will discuss in more detail next week. But now I just wanted first to give you the top-down view. And the easiest way to look at these things is to take a harmonic oscillator function. Because with a harmonic oscillator, we know that if we have a trial function like this, we have a local energy, which takes a simple expression. And then we can calculate the energy. This is just the integral over the local energy multiplied with the probability distribution, which is this function squared, and divided by the norm. And in that case, we have an analytical expression, which is simple to set up. And then you see that when you want to calculate the gradient here, you just take the derivative of this quantity with respect to alpha. And that gives you the minimum. So your minimum value here is where this quantity is equal to 0. If you require that this equation here is equal to 0, you get alpha equal to 1, which is what we started with at the beginning of the semester. So essentially what we want is the gradient of the expectation value of the energy. And this is the quantity we now want to evaluate. Another thing which is very useful to see is that this quantity here is a positive quantity. So the second derivative is always positive, which means that when we now go to a multivariable quantity, this can be translated later into a matrix. And this is then a convex optimization problem. So there is a minimum. So we know that when the second derivative is positive, this is normally indicating that we have a convex function. So when we have more variables and we calculate the Jacobian, then you will see that the Jacobian matrix is a matrix which is positive definite, which means that all the eigenvalues are larger than 0. So this is, if you just think of this now, this is in essence what we need to do. So that's the basic message. So I just put in some exercises which you can test with your code as well. You can then repeat it for n bosons or electrons and what is the optimal value for alpha without taking into account any interaction. Another thing which is also done in many of these variational Monte Carlo calculations is to optimize the variance. And one of the reasons, so many people have often made a variational calculation where you put some weight to the energy variation and some weight to the expectation value of the variance. Now, the nice thing with the variance is that we know its value. If you have the exact function, the variance is exactly equal to 0. So, but this becomes, as you will see pretty soon, this becomes much more complicated from a Monte Carlo calculation point of view. So what I'm going to give you now are just the expressions, and then we are going to go back and see what we need to code. And then we're going to derive these expressions. So now I'm setting up the expressions you need. So this is now just a compact notation I have opted for the derivative of the expectation value of the energy with respect to the variational parameter. So in this case, we're just looking at one parameter. So then we just don't need a gradient. But in general, you will have many parameters, and then you have a gradient. So another quantity which I defined here is this psi with a bar. This is the derivative of the trial function with respect to the parameter alpha. Then, and this is an equation we are going to derive, but I'm just stating the equation, and then we will do the derivations in just a few moments. So if you now think of the gradient of the energy or the derivative of the energy, this is now going to involve three integrals. One integral here, which has a derivative of the wave function, so this is this expression you see here, divided by the wave function. Now you know that this function here, if you look at this one and you divide this by psi of alpha, this can actually be written as a derivative of the logarithm of the trial wave function. This is extremely useful because many of our wave functions are given by exponentials. So would then have d of ln of psi of alpha because you have 1 over psi alpha, which is this quantity here. So this is an integral we need to evaluate. And this is why it becomes more complicated. And then I need to evaluate this integral, and then I have the integral over the energy. And this will be done with Monte Carlo samplings. So you will have 3 new integrals. Actually, this integral is one you have, but these will be the 2 new integrals which we need to bake into the program. So this complicates life because we are going to run these integrals stochastically. So we're going to calculate them with a variational Monte Carlo approach in the same way as we have been doing till now. And then we have the difference between 2 quantities, which in general have an error because we're doing a Monte Carlo sampling. So we can have a sensitive difference between these quantities here. But this is the quantity which we now reuse in setting up the gradients. So we need 2 additional integrals. And there's an exercise here, and we are coming back to this in the lecture notes. This is a little bit boring case because that will involve 7 integrals. And this is the reason why you don't optimize the variance, even though you know that if you have variance equal to 0, you know you have the exact wave function. But the main reason is simply because it involves more computations. So the code which you have is something we will come back to. But what I want to do now is to go back to the whiteboard and then look at some of these technicalities which we need to take into account. And we will continue with this topic next week as well. And most of you are now in the stage where you're still setting up the brute force / doing importance sampling. So this would be a programming element which you should start thinking of, let's say, next week sometime. Okay, so let's now bring up the optimization part. So if we now look at the task which we have at hand, we have a expectation value of the energy, which is now the expectation value of this local energy as a function of the variational parameters. And in our case, this is this multidimensional integral, d of r, where r is an element in a specific domain of variables. So we have this probability distribution, which depends on these parameters alpha. We have r, and then we have the local energy, which depends on the positions of the particles and the variational parameters. And just to quickly remind you, this P of alpha of r is then simply the quantum mechanical probability distribution for the trial wave function. And then we have our norm here, our d of r, and then psi of t squared. So when we now look at the calculations, what we are going to just illustrate here in the graph is a parameter alpha, which now just depends on one variable. So there's just one alpha variable. And typically what you have seen till now is that you calculate the energy as a function of this variable alpha. This is the expectation value of the energy. In our case, we have only one here. And then you would get something like this. And this is a quantity which we will label with an alpha hat, which is also something we will sometimes call the alpha optimal. So alpha, when we have a hatted quantity, that is the optimal value. Now, at this point here, that is where the gradient with respect to alpha of the energy expectation value. So I'm going to, when I don't say anything, then this quantity which you see here, I will just call this for E. Okay? Just to shorten down things. So this is now the gradient of E with respect to the parameters alpha. And typically what we would do then when we run the Monte Carlo calculation, we would run extensive calculations for the different points. And then we could make a plot, and then by interpolation, we could find this point. The only problem is that if I do, let's say, 10 to the 18th Monte Carlo cycle here, 10 to the 18th, etc., and I have 10 points, then I'm going to do 1 billion Monte Carlo cycles. Instead, what I could do now is to run a calculation where I simply do 10 to the 4 here. And then I calculate the gradient. So I get a delta alpha V, and then I may find a new point, and then I do another 10 to the 4. And then if I'm lucky, my gradient here is actually equal to 0 at this point. This is ideally what we want to have, okay? Or something which is close to 0 after a given number of iterations. So we are going to perform a set of iterations, and the ideal then is that we run with few Monte Carlo calculations, and then we reach this point. That's when we mount our big Monte Carlo machinery, and then we can do something like 10 to the 8th. So if I'm lucky, I need only some 5 to 10 steps to reach this point here, which means that I've only run something like 100,000 cycles. And then I run my 100 million cycles there. So that means that roughly I'm calculating this quantity with 100 million CPU Monte Carlo cycles instead of running 1 billion in a brute force way. So this becomes very important because many of these Monte Carlo calculations are really time consuming, and they run over long, long times. So let's now look at how we would set up the mathematics for this. And then we are going to look into codes a little bit later. So the mathematics of what we want to do now is to calculate. So I'm just going to introduce these shorthands, which I'm going to use. And I'm just going to call this E of alpha. And sometimes I drop the alpha variables. And then I'm going to need the gradients of E with respect to alpha. I'm just writing it like this. And this is a quantity which I will just call G for gradient of alpha. Now, for the simple one-dimensional case which we have of alpha, then obviously this is just a first derivative. So we are now going to look at the alpha going over to just a scalar variable. So that means that this G of alpha is now going over to G of alpha. And my alpha optimal, where I have the minimum, is actually going to just be given by alpha here, alpha hat. So what I'm going to do now is to make a Taylor expansion of this function which I have. And I'm going to make a Taylor expansion of the energy around the optimal value. So what I'm going to say now is the following. I'm going to introduce some notations here. So because I want to prepare for a Taylor expansion. And what I'm going to do now is to derive Newton's method, or Newton-Raphson's methods, as it should be called more correctly. So I have an alpha minus an alpha n, and this alpha n stands for iteration n. So I would start this process iteratively, and then I repeat this a given number of times. So I'm going to call this quantity for B of n. So these are just notations. And I'm also going to write this G of alpha as a G of alpha n. And I'm just going to put a subscript G of n here. So the whole idea, if we now go back to the figure which we put up on the previous slide here, is that you would start with a value here, which we would call alpha 0. And then we do a new calculation here, which could be alpha 1. And then gradually, as we move down, we reach the optimal value. So we would continue this with a given number of iterations till the gradient is 0. So the basic mathematical algorithm for doing this is to set up the Taylor expansion around the optimal value. I'm also going to introduce some more notations. So since I only have one parameter, then this E of alpha is now going to be replaced by a delta of alpha, and it's going to be evaluated at alpha n, and I'm simply going to call this quantity for an A of n. So now I have a scalar quantity. So I only have one alpha value. So now I make a Taylor expansion. So we Taylor expand around the optimal value of alpha. So that means that my Taylor expansion, I have the energy at this optimal value. And this is now given because I'm Taylor expanding around alpha minus some alpha of n. So this is going to be given by an energy E of n, which, as we said, is the same as E of alpha n, plus, and now I have the quantity B of n. So I have alpha opt minus alpha n, which we also label as a B of n. I have my gradient, this first derivative, G of n, right? And then I keep going here. So I get 1/2 times this quantity A of n, which is the second derivative. And then I have my alpha minus alpha of n squared. And then I have my higher order terms, because I'm now iterating around alpha minus alpha of n here. And these are just higher order terms squared. So this is as a scalar quantity. We just have one alpha. So if I now replace this with more alpha values, with more than one alpha, then I need to calculate the gradients. And then this expression here is now going to be given by still the energy at around this optimal value. It's going to be given by this energy E of n. But now I need to be a little bit more careful, because the energy is a scalar. So that means that if the gradient now is a vector, then I need to calculate an inner product between two vectors. So that means that I have my gradient at value n multiply do it transposed. So this is just an inner product. And then I have the vector B of n. So with this now is just alpha minus alpha n vector. So this contains now all the parameters. Plus, and since this now has to be a scalar, I need to set up the vector B of n, t, multiplied with A, which is now a matrix. And this is a Jacobian of B of n. Plus these O terms, where I have now B of n to the power of 3 or higher. Okay? So I hope you don't get offended if I just start by doing a plain Taylor expansion again. So if you now have, suppose you have two parameters, let's do that, eh? So suppose now alpha is given by some alpha 0 and alpha 1. So we have two parameters. Then this A of n is going to be a matrix, which you'll probably encountered as a Jacobian. So this is going to be given by the derivative of E with respect to alpha 0. And this is evaluated at alpha equal to alpha n. So we should put the subscript. So this alpha of n now is now given by alpha 0 n and alpha 1 after iteration n. And then I have the cross terms. So I have the second derivative of E with respect to alpha 0 and alpha 1. And this is again evaluated at this set of values, alpha of n. I'm just putting up a matrix here. And then I have the other cross term where I have d alpha 1, d alpha 0, evaluated alpha equal to alpha of n. And then finally, I have the other diagonal term here, which is d alpha 1 squared, evaluated alpha equal to alpha of n. So remember now that this function E is a function of both alpha 0 and alpha 1. So when I put this label here, it means that I have to calculate this function both for the value alpha 0 at the nth iteration and alpha 1 at the nth iteration. So if I now neglect, so I neglect higher order terms. So I neglect the terms of b of n cubed. So b is just the difference between the optimal value and the iteration which we are looking at. So that means that if I do that, this is the value I want to reach. And then I have my E of n plus this G of n. So let's keep these as vectors now, plus 1/2 of B of n transposed of A of n of B of n. So what you see now is that this is a object, which if I now think of these as vectors, this is going to be a constant plus some vector G times a vector X plus, I'm going to put vector signs here, plus 1/2 of X transpose. And then I have some matrix A, which I haven't defined here, times some vector X. So when we are now going beyond the scalar, this is actually what our equation looks like. Now you can now calculate the derivatives of these quantities with respect to X, because this is what we want. So what that means, if you look at this expression which you have here, and you take the derivative of the gradient, then you see immediately that if I do that, if I do this d of f, d of x, and I want that one to be 0, this is just going to be the same as ax plus this quantity g, and we want that to be 0. So that gives us simply that x is equal to a minus 1 times the gradient. Okay? And the thing is that g and a are known at the iteration. And since I'm using x instead of alpha here, then I should actually write x of n here. So when I perform an iteration, these are quantities which I can calculate. So it means that my x of n is simply given by these quantities here. So let me just give you a simple example, which you probably have seen before. And this is just to exemplify what we are having here. Suppose you have a function of two variables, x1 and x2. And you could think of this function as being given by this example here, x1, x2, plus 10 times x2 squared, minus 5 times x1, minus 3 times x2. Now I can rewrite this in terms of matrices and vectors. So if I define now a vector x here, which is given by x1 and x2 as variables, so x1 and x2 are scalars, then I can rewrite this function which you see here. So this function is equal to 1/2 of x transpose. And the matrix A, when you look a little bit closer at it, is going to be 2, 1, 1, 20. multiplied with, and then I'm writing out x1 and x2. I can write it more compact like x. So just keep in mind that what you have now is x1 and x2 here, and x1 and x2 here. And then this is given by minus. And now we see that there is a 5 times x1 and a 3 times x2. So that means that what we would have then is a minus, and then there is a 5, a vector 5 and 3 multiplied with x1 and x2. So this one, if we now go back to the equation which we had here, in this specific form, that would be that the quantity which we had there would play the same role as this gradient which you have here. So this quantity here would then just be an example of that vector g which we put in before. Okay, does that sound reasonable? And then if you want to find the minimum of that function, you would have to calculate the minimum with respect to x1 and x2. So I hope you don't get offended if I now actually do this. So what I want now is that d of f of d of x equal to 0. So in our case, then we would need d of f of d of x1, which is 0, and that's the same as 2x1 plus x2 minus 5. And then we have another equation for x2, which we want to drive to 0. And that is the same as x1 plus 20, x2 minus 3. And then I can actually start an iterative process where I now start with a guess. So our guess for an iterative process, and this is an overkill for this specific case, because you know that you can solve these equations. I guess this is something you saw back in kindergarten, almost. But you could say that, okay, I don't care about what I learned in kindergarten, and I've now heard about these Newton-Raphson methods, which is so fantastic, so let me implement that one. And what we could do then is simply to start with a guess, x0, which could be something, yeah, this is just a number, minus 3 and 1, just to give an example. So what you would end up with then is an iterative scheme where if you now look at the equation for the energy, so what we need, going back to what we are doing now, so what we need is the gradient with respect to the parameters alpha of the energies, and we want this one to be at a certain point, alpha optimal, and this is the one we want to have equal to 0. So what I'm going to do now is to say that my alpha optimal is the outcome of iteration n plus 1. So this is a quantity now which I want to have equal to 0. So I perform these iterations, and this is something I want to be 0. And if I look at the equations which I had, this is going to be given by my gradient, evaluated at iteration n. So this is now the same as the gradient with respect to alpha here of E at alpha n, and plus this quantity which I call A of n times this B of n. So this is a matrix and this is a vector. I'm skipping the vector signs. So this quantity is the same as alpha of n minus actually alpha n minus 1, because that's my previous iteration. So what I'm going to do then is then to set up an iterative scheme. So let me just remind you of these parameters. No, sorry, beta n. No, sorry, this is alpha. I was a little bit rushed here. So beta n is actually alpha n plus 1 minus alpha n here. So if I do that, what I'm going to have is an iterative scheme where I have alpha n plus 1 minus alpha n is going to be equal to minus this an inverse multiplied with g of n. So this is a matrix. So the only thing I did now, I'm just plugging in this b of n, the expression here. I want this to be 0. And then what I have is a quantity I can evaluate. I can evaluate this quantity. So that means that I get a scheme where I have alpha of n plus 1, the optimal value, which is alpha of n minus an, the inverse of this quantity of g of n. Now, if you think back to Newton-Raphson's method, the way you have seen it, so what we have done here is actually nothing but deriving Newton-Raphson's method. So Newton-Raphson's method is based on a Taylor expansion around the optimal value. And you keep only terms to the second derivative. So this is nothing but Newton-Raphson's method. And if I can calculate the inverse of that matrix, then, and I can calculate the gradient easily, then I actually have the solution to the problem. So you would start with a guess, and then you would just keep going till you reach the final point where this gradient is equal to 0. So what we are ending up with then is a recipe where we solve iteratively with a guess. Starting with some alpha 0, a guess which we have with alpha 0, and repeat till we have, since these are vectors, alpha n minus 1, alpha n plus 1 minus alpha n here, and then we take the norm 2 here, is less than a specific quantity epsilon. And this could be, let's say, 10 to the minus 5. It could be 10 to the minus 8. It's something which we set. And if that condition is fulfilled, then we say that the process has reached its optimal value here. So this a of n is a second derivative, and it's common to replace that second derivative with a constant. So a of n, which we have here, is a Jacobian matrix. When we have more than just one variable, is a second derivative. And it can be difficult to evaluate and time-consuming, not the least. Can be difficult and time-consuming to evaluate. So what we are going to discuss are different strategies for actually evaluating or replacing the evaluation of this second derivative. So it's common, and this is the simplest common. This is the very simplest approach. To replace by a constant. And in the machine learning literature, this is called the learning rate. To replace by a constant. And next week, we will see recipes by which we can replace this constant with something which has some memory or some knowledge about the gradients themselves. And there are different ways of doing that. One is called steepest descent. Another one is called conjugate gradient method. But then we also have Broyden's method, which we are going to use in these applications which we have here. So this is a second derivative. And we would then replace this a of n with some constant, which we simply call gamma of n. And gamma of n can be a constant throughout the calculations, and normally it's a small number. Sometimes it's cheaper actually to run the calculations with an array of these constants. which is pretty common in machine learning. So if we do that, then we have a recipe here where alpha optimal is given by this alpha of n plus 1, which is then alpha of n minus this gamma of n multiplied with a gradient. So this is the simplest possible recipe which we can end up with. Now, the question then is, how do we actually find this optimal gamma? So suppose we use this recipe here now. You can actually find a specific condition on that. So how do we find, suppose now that we have replaced the second derivative of the expectation value of the energy, and you will see that the expectation value of the energy, if I want to calculate the first derivative, the gradient, I need to evaluate 3 integrals by Monte Carlo sampling. If I want to calculate the second derivative, there are going to be 6 to 7 integrals, which I have to evaluate by Monte Carlo calculation. And I don't want to do that, because that's going to require many, many more cycles. So how do we find an optimal gamma of n? So what we can do now is simply to make a Taylor expansion around. So we perform a Taylor expansion of the energy evaluated at alpha n minus gamma of n of g of n. So we are free to Taylor expand around this value here. And when we look at it, this is just going to be the value of E of n minus, and then I'm going to have this gamma of n. I have my gradient, and now I'm putting the transpose here times the gradient transpose. So remember now that my alpha of n plus 1 is actually given by alpha minus this gamma of g of n. So I'm just making a Taylor expansion. And then I have a higher order term, the second derivative. So I'm going to have a gamma of n. And then I have my g of n of t times this lovely matrix, a of n. And then I have g of n. And then I have high order terms in terms of gamma, or this quantity alpha of n minus gamma of n of g of n to the power of 3. So this is my Taylor expansion again. This quantity here, that depends only on the previous value of gamma of n minus 1, because that was the value I calculated previously. So in order to find the optimal value, and what we're also going to do is just to drop this one, then I can calculate the derivative of this energy with respect to d of gamma of n and require that to be 0. So if I do that, obviously here I just have gn times gn, and here I'm going to have 2 times gamma of n, and then I can isolate the terms. So what I'm going to get then is gamma of n is given by g of n of t of g of n of gamma of g of n times a of n. So this is a vector times a matrix in principle. So this is in principle a matrix, and this is a vector. And we have to evaluate these quantities at each iteration. So this is a way by which we could find an update of the parameters gamma. This is actually a method in the optimization theory, which has its name, and this is called the steepest descent. So this is one of these famous methods. So if I just keep a constant rate here, if you look at this expression which you have here, this one is just called a plane gradient descent. Plane. If I just replace gamma with a constant. Then the next method, which is a little bit more fancy, is called the steepest descent. And this opens up a whole plethora of methods which deal with the optimization problem. But you see now that at the end, what we are going to do now is simply to calculate these quantities gamma of n, either by setting them as a constant or trying to find an estimate of what the second derivative actually looks like. So if you, if now this basis, and we're coming back to that next time, if this one basis here is an eigenbasis of this one, this equation simplifies further, but we are coming back to that next time. So what we want to do now is to avoid calculating the second derivative. So we want to, the strategies which we are going to implement now, so we want to avoid to calculate this matrix A of n, which is now the second derivative with respect to the parameters alpha of E of n at an iteration n here. Because this is going to be complicated and involved. Now, what we need now, and we didn't discuss the codes yet because I want to bring that up next week. So we need to show, and this comes next week, to show. So let me just end today with setting up what we need to show next week, is that the gradient of d of alpha, of the energy, with respect to the parameters alpha, are going to be given by two integrals. So there's going to be a factor of 2 here, and this is multiplied with an integral, which runs like this. It's going to be 1 over the trial wave function, psi of t of alpha, multiplied with a derivative of psi of t with respect to alpha, so that goes in the denominator, times the local energy. So this is an expectation value. This is one integral. And this is what we will show next week. Minus the expectation value of d psi t with respect to alpha, multiplied with 1 over psi of t of alpha. So we're going to evaluate this integral by itself. And this has to be multiplied with a new integral. And this integral is something which we have already calculated. So we are going to show that this is the way the gradient is going to look like. So this is one integral. And this is also an integral, which are evaluated. So these integrals are evaluated by Monte Carlo sampling. That means we are going to stochastically evaluate multidimensional integrals. So we will start with a guess for the parameters alpha. And then we hopefully then, after some few iterations, we will reach the holy grail, which is this quantity equal to 0. So for those of you who are familiar with machine learning, this one is the cost function or loss function. And this plays the same role as the gradient of the cost and loss function. If you then replace this quantity here with a neural network. So you can think of the energy expectation value as your cost/loss function. So next week, we are going to derive that equation. You can take a look at the equations which we have in the slides this week and try it yourself. And when we're done with that, we are going to go through an example code. And we're also going to discuss other methods like steepest descent, which we went through now, and conjugate gradient method. But at the end, we are going to make life very simple for ourselves, and we are going to use Broyden's method, or we are going to be even simpler. We are just going to play around with different learning rates or these different parameters gamma, and just perform a simple brute force gradient descent. And at the end, this is often what many practitioners end up doing as the first approach. So I hope I gave you the basic overview of what we're actually going to do. And then next week, we will set up the integrals and show you an example. There's a code example in the slides this week, which we will go through in detail next week. And then you have the next ingredient. After that, our next ingredient is to use statistical resampling methods to evaluate the variance in the best possible way. Because if you run stochastic calculations, if you don't provide an error estimate, which means you don't provide the square root of the variance, nobody will buy your results. Because this is a stochastic method, and they have an error which you can calculate, and that's the standard deviation. So there are ways to calculate the best possible approach to the standard deviation. And some of these methods are methods you have met before, like bootstrap, jackknife. But for this type of technology, which we are dealing with, there's another method, which is called the blocking method. And this gives you the final thing before we have parallelization. And when we have all these gritty, nitty details, then what you have is as close to as possible as a professional Variational Monte Carlo code. You guys ready for a small break before we go up and have our lab sessions? Is that okay? And we just go back to that room at the center, because it's free today as well. So I'm gonna stop the recording.